Recording. All right. So we were talking about energy methods, right? I shared that video with you. If you haven't watched it yet, I highly encourage you to do. That's a great example of, or a great demonstration of energy method. I wish I could teach that way, but that's a very different level of teaching. But we can still enjoy watching him teaching that topic. So we're talking about energy method, right? And we started with the general concept. How do we use energy method to find the relationship between velocity, to basically analyze the velocity of the motion, find the relationship between velocity and displacement or position of a particle. Then we moved forward, right? In the last class, I talked about a special case, a case in which we don't really have any, I think I brought a couple of slides here from before, a case in which we don't really have any non-conservative force, meaning that all the forces we're dealing with are conservative forces. So non-conservative force, we said in our case, we basically talk about friction. So if we don't have any friction, basically we can use principle of conservation of energy, telling us the total energy is always constant. You have potential energy, kinetic energy, whatever happens, the total is the same, just one is converted to the other, depending on where you are or at which stage in the motion you are studying that specific particle. So we said T1 V1 is equal to T2 V2, T being kinetic energy, V being potential energy. Now, said unfortunately, textbook use V for potential energy and V for velocity. So I try to distinguish them by writing the V for potential energy a little differently, and I try to stick to that type, to that writing, I would say, or standard. When you use conservation of energy, three types of forces or potential energy of three types of conservative forces: potential energy of a constant force, potential energy of a weight due to gravity, and potential energy of a spring. And we said the difference here is that when we look into potential energy, for instance, of a weight, we have to establish some zero potential line. Right? So once you establish that, every time that you want to write the potential energy for your particle at any given moment, you just find the height from that zero potential line or date. Right? We went over one example. I didn't bring it here. This is the next example. I basically put the problem statement there and kind of reviewed what the problem is asking, and that's where we're gonna basically start today. That's where we, at least I'm planning to pick up the whole conversation that we were having about the energy method. Now in this problem, right, we have a 1 kilogram collar, right? It's in position 1. Right? The tension in the spring is 50 Newton, and it's unstretched. Right? When we're at point 1, the spring is unstretched, and the tension is 50 newtons. Sorry, it's not unstretched. The tension in the spring is 50 newtons, and we are also given the unstretched length. Or if it's unstretched, the force would be 0, right? So there's some force at point 1, and we also know the unstretched length of the spring, position 1. Then we pull this collar all the way to the right to position 2, right? And then let it go. Right? We release that collar. Now what we're asked to do is that we're asked to find the velocity of this collar, or mass, moving mass, when it returns to position 1. So if I pull it all the way this way, let it go, this spring is under stretch. If you think about it, the length is 260 millimeters, and that length is definitely more than 260. We let it go. The spring is always, we said the spring is always trying to go back to its natural position. Now, if it's stretched, it tries to go back to its natural position. If it's compressed, also it tries to go back to its natural position. So the direction of the motion of whatever is attached to the spring is determined by whether the spring is under stretched, is stretched and it's trying to go back to its natural position, or it's compressed and it's trying to go back to its natural position. Natural length better than position, or stretch length. So how do we deal with this? Right, we start with, well, there is no, we are told, hopefully somewhere, that apparently not clearly, let's maybe I have to emphasize that the bar is smooth, right? So there is no friction, there is no non-conservative force, there is no kind of force that takes energy out of the system. And so the system is, the energy is conserved. Now, having said that, we start from where we typically start when we are dealing with problems, as we saw in previous example, when we are working with a problem that there is no non-conservative force. We can apply principle of conservation of energy, right? So T1 plus V1 is equal to T2 plus V2. Now let's just find out each of these values. So T1 there, let me follow my way of writing, T1 and V1. T1, well, we are trying to find the velocity at position 1 when it returns, when this color returns to position 1. So obviously there is some velocity there, and we already know there will be, even if you think about that, this color starts sliding from position 2 coming back. So when it gets to point 1, obviously it has some velocity. We don't know that. That's what we're trying to find out. So 1/2 m v1 squared. Mass is 1 kilogram, so I can just plug that in right here. So it's going to be 0.5 v1 squared. Potential energy, well, I need to define some zero potential line. So let's just define this as zero potential, right, or data that I have. I might be able to write a little bit of it. There you go. So if that's my zero potential line, looking at this color at point 2, what would be the potential? Let's write it this way. V1 due to gravity, and V1, I'll have to follow my own notation, my standard. V1 due to gravity and V1 due to spring. We have two sources that are that they can store potential energy, or they can cause, or they can add to the potential energy of this color. Now, what would be the potential energy due to gravity? I think, assuming that that's my zero potential, at point 1, what would be the potential energy due to gravity for that color?
0.
It's 0. Exactly. Thank you. It is 0. There's no height, right? I'm exactly on that line, so that's 0. I know it's not easy to talk on Monday, 8 a.m., right? So that's much more appreciated and more than usual. All right, so for the spring, to calculate the potential energy of the spring, right? I actually gave you that here. There you go. So it's right there. It's in point 1, so 1/2K S1 squared. S being how much the spring is stretched or compressed from its natural length or unstretched length. Remember that. That's very important. So I write it as 1/2K S1 squared. Now K, I don't know. S1, I also don't know. So let's see how can we figure this out. What am I given about this spring? I'm told that the tension in this spring at this position, at position 1, is 50 newtons. So just look at the collar at position 1, the spring attached to it, totally vertical, is 300 millimeters from where the collar is to where the other end of the spring is attached to. The force in the spring is 50 newtons, and the unstretched length of the spring is 216 millimeters. These are two pieces of information, or these are the information I know about the spring at position 1. Let's see how can I use these to find what I want. What do I want? I want the spring stiffness K, and I want to know how much the spring is stretched or compressed. Let's just start with the second one. How much the spring is stretched or compressed? S1. How much is that? Stretched 40 millimeters, exactly, right? The length at position 1 is 300 millimeters, and we know the unstretched length of the spring is 260. So spring is stretched by 40 millimeters at this point. So 300 minus 260 is equal to 40 millimeters. That's S1. We have to find K, right? The stiffness of the spring. Force in the spring is Ks. Stiffness times how much the spring is stretched or compressed. So F, I'm going to write it as Fs is equal to Ks1. I know what S1 is now, right? It's 40 millimeters. I know what F is 50 Newton in the spring at this position. So I can find the spring stiffness. I can find Fs over S1. That'll give you K as Fs 50, S1, let's convert that to meter. This becomes 0.05 meter, right? So it becomes 0.05. Did a bad job managing space here. K is equal to 50 divided by 0.04. That'll give you 1,250 Newton per meter. And so keep this as a side that we had to calculate these from the given information problem given in this information given in the problem statement. So now we can actually calculate the potential energy at position 1 because of how much the springs are stretched. Right? So that becomes 1/2, 1,250. S1 is 0.04 squared, whatever the number is. And there is no constant force. No force is applied to the system aside from the force of the spring that we have there. So out of these three, well, there is no potential energy of a constant force because there is no constant force when I look at the system as a whole. I took into account the possible potential energy because of weight, 0. I defined my zero potential line in a way that it's 0 at position 1, potential energy because of weight. And I calculate the potential energy because of the spring. Right? So that's the left side, right? T1 and V1. Let's look at T2 and V2. Right? This one, let's wait here. T2, what is T2? Kinetic energy at position 2, given the information in the problem statement.
Zero.
It is 0, exactly, right? All right, because we release it from rest. So 1/2 mv2 squared. Well, that is 0. All right, so the whole thing is 0. No kinetic energy at that moment. We just release it from rest. Potential energy, V2, let me write this the same way I did. V2G is equal to, and V2S because of spring. I'm just trying to distinguish different potential energy sources. So what is V2 or potential energy at point 2 due to gravity or weight? Still zero, exactly. We are in the same line, like going back and forth. So that's still zero. Spring, well, 1 over 2 K S2 squared. Now, what is S2? What is the change in length or how much the spring is stretched when we are at position 2? K we already know from before. K is constant. Once you find K for a spring, that just is the same. It's a property of the spring. So it doesn't matter what information you use to find K, your K is always the same. Just keep that in mind. It's K is a property of the spring. It's spring stiffness. As long as we don't stretch the spring too much that it deforms, or compressing too much, or compress it too much that it's out of its range, that the range is supposed to be compressed, K is the same. And we're dealing with linear springs here, so we are fine. Just 1K always for the spring. We have to calculate S, or S2 better to say. S2 would be whatever is the length of the spring at position 2 minus whatever is the unstretched length of the spring. Now, unstretched length of the spring, we already know that it's 260 millimeters. So we have to find the length of the spring at position 2. Now, that can be found. We know if you look at the triangle there, we know 300 millimeters is the height, 600 millimeters is the other side. So it's a right triangle. You can find the hypotenuse. You can find the hypotenuse, right? This length right there, it's square root of 300 millimeters plus 600 millimeters. Or probably it's better if you write it in meter. 0.3 squared plus 0.6 squared. So this, let me write it here. S2 is square root of, let me write it in meter. 0.6 squared plus 0.3 squared minus, right, this is the current length, minus the unstretched length of the spring, which is 260 millimeters. All right, just change that into meter 2.26. So this is the, just don't get lost there. Unstretched length, right? Because S is representing how much the spring is stretched or compressed. Keep emphasizing that because that's the probably somewhere that mistakes happen. So if you do that, your S2 becomes 0.411. If I did not make any mistake there, meter. Let's also keep it there. Once you know S2, well, 1 over 2 K is constant. 1 over 2 K is 1250. 0.411 squared. So pretty much you have everything you need. If you put things together, T1 plus V1 is equal to T2 plus V2. From the left side, you get 0.5 V1 squared plus, so that becomes from star, let me put it here so we know which equation we're talking about. This becomes 0.5 V1 squared plus 1 over 2, 1250 times, what was the length? 0.04. 0.04 squared is equal to no kinetic energy, no gravity, potential energy due to weight. The only thing we had was 1 over 2, 1250 times whatever the spring, 0.411 squared. 11 squared. The only unknown there is just V1. So you can find V1 from there. Just move things around. What I got was 14.8 46 meter per second. Hopefully that's the correct number. Let me know if you get something else. All right. So point of this problem, pay attention to how much to parameter S, right? It represents how much the spring is stretched or compressed. It does not represent what is the current length of the spring. Don't make that mistake. Right? It tells you how much the spring is stretched or compressed, knowing the initial length. Well, you have to know the initial length and the final length to figure that out. All right, question on this one. Right. Now, one good thing about the energy method is that it allows us, it lets us solve problems or deal with systems and motions that is typically very difficult to deal with using Newton's method, as we call it, like drawing free body diagram and looking into forces, how do they change. Sometimes that method can become very, very painful and difficult for some complicated systems. And there are cases that you just want to look into velocity. You want to find the velocity, that's all, at a given moment. So energy method does that for you without you going through drawing free body diagrams and making sure that everything is there, directions are correct, your coordinate system is correct. So there are so many things that can go wrong using Newton's method. You've had some experience by now. You have some experience dealing with problems, solving problems using Newton's method. So this makes solving some specific situations much easier, especially if you're just looking for how the velocity is changing or what is the value of velocity or how fast that object is moving. Right? And then you can use that to actually look into forces, like the example we did before this example. We found what is the velocity of that color passing through that tube, right, at a specific point, and then we looked at the object or particle or that color or the mass, draw the free body diagram just for that specific position, and we could find how much force is applied by that color to the tube, right, like previous example. So that can help you a lot. Now, the next example is one of those examples that it is much easier to solve it with Newton with energy method. Right? The next example I'm going to go over. Now, all these problems you can solve with Newton's method, most probably. I haven't really tried most of them. I haven't tried to solve them with Newton's method, but you basically can. Right? It's just going to be much more difficult and a lot of much more assumptions or different things you have to take into account to just find the velocity that you could find using just energy method. All right, let's look at another one without the spring again. And just looking into some pendulum. That's some kind of thing that you deal with. You have to be a little more comfortable with when you're dealing with energy method. Let me draw the figure for that. It's straight line there. Basically the support. You have some hinge here, and then you have a mass attached to that support. Let's see if we can draw this as, that was not something. There you go. You have this mass M. It's attached to some ceiling, some support hanging. So this is a pendulum swinging back and forth. Right? This is your horizontal line, let's say. vertical line. So that does not look like a vertical line at all. I'll just draw it like this, or close to that at least. This is the vertical line. If you think that's exactly where the vertical line is. And this angle, how far your pendulum is from this vertical line, is theta. The length of this thread that you've used to connect or hang this piece, this mass M, is L. And then you have this pin here. Just to make it as complicated as possible, they gave you a pin right there. So this is in front of a wall, right? The pendulum is swinging back and forth. And then on the wall, you have a pin, right? Some nail put on the wall, or some type of pin screwed to the wall. So when this pendulum is swinging, when it gets to vertical position, right, the thread is going to hit this pin, and it's going to, the pendulum keeps going up. The energy is still there, so the kinetic energy keeps or pushes this pendulum upward. But then the thread is going to be folded. Right? This is what I'm trying to picture here. So when you get to this point, the thread is there, and then let's say you get all the way to here. I was hoping that this is going to detect that it's a circle, but apparently I'm drawing the circle so badly that not there. So that would be the M mass. So we release it from this side, it swings till it gets to a vertical position. At vertical position, there is a pin in the middle right there. This length is L/2. This length here is, let me use a different color so it's not confusing that one. So this length here is L/2. The pin is exactly placed in the middle of this thread. Hits there, well, the thread stays vertical. First half of it, the second half, it bends all the way, or it goes all the way up because of the kinetic energy of this mass that is trying to basically continue the motion. That's the situation. Complicated enough. All right, so the mass, let's put the problem statement this way. The mass M is equal to 2 kilogram, and the string length is L equals to 1 meter. Right. This is example that is trying to show you how we just care about where the particle is at the beginning and at the end. We don't care about what is happening in the middle. Remember, this path independent, the whole story of kinetic energy, of energy method, especially when we don't have a non-conservative force like friction, is totally path independent. The string length is 1 meter. The ball is, I can write a little better. The ball is released from rest in position 1. This is position 1. When the string is vertical, it hits the fixed pin, right? Now, part A is asking you to find the minimum angle, find the minimum angle theta necessary for ball, necessary for the ball to swing to position 2, to swing to position, I don't know what I'm wrong there, position 2. This being position 2. Right. From 1 to 2. Now, if you wanted to do this with Newton's method, things are going to get very messy. You know, you have to track the motion. You have to figure out so many things that you probably don't even know. For this case, when we're using energy method, it's relatively straightforward. You don't care about what's going on in the middle. Right? What you care about is where we are at position 1 and what's going on in position 1, and where we are at position 2 and what's going on in position 2. Path independent. So I write the T1 plus V1 is equal to T2 plus V2. My principle of conservation of energy. Now looking at point 1, let's just T1 V1. Looking at point 1, we start with kinetic energy at point 1. Well, we are told that the ball is released from rest in position 1. So no velocity, that'll be 0. Right? Released from rest. V1, potential energy, I have to come up with some 0 potential. This one, I'm going to take it, I'm going to take the 0 potential line here. Does it matter where you take it? No. You can take it anywhere you want, as long as you can find the height or the distance of your particle in position 1 and position 2, in position 1 and position 2, or 2 positions that you're studying, right? From that line. So I put 0 potential there, or datum there. Having that line as 0 potential, what would be the potential energy? Well, there is no spring, so I'm not going to write that. What would be the potential energy in position 1 due to gravity? Given the information I have in the problem, I know the length of the string is L. I know the angle it creates with vertical position is theta.
Would it be negative L cosine theta?
That would be negative L cosine theta. Very good. Let's just clarify. Let's just make sure that everyone follows. So we have this here. This is where we are. This is point. I'm going to call this, just to have some name, I'm going to call this point O. This is where my mass M is. This length is L. Now, when this swings, right, it swings this way, right, generally speaking, at least up until here. Now, this L is this length also, right? It's a thread. It's like following a circular path. So anywhere on this path, the length is L. It's the radius of this circle, assuming that it's a circular motion, at least for this part. Now, that being said, what I care about is, if this is the 0 potential line, what I care about is, let me do a better job drawing this. That did not help at all the way I draw it. If you draw it like this, right, up until midpoint. After that, it changes. This is length L. And here is the height I'm looking for. This is zero potential, and this is the height I'm looking for. H, let's call this H. This height, looking at this right triangle there, this triangle here, try it as good as I can. This is a right triangle. This angle is theta. The hypotenuse is L. So what I'm trying to find is H. H being the adjacent. So H, or you can start with the definition of cosine. Cosine theta is equal to whatever is adjacent over hypotenuse. That means H is equal to L cosine theta. We are looking at this mass at position 1. At position 1, that's where the height is. Height being the distance from zero potential. I took zero potential all the way at the top. So the distance it has from zero potential is H. Now, that H is negative because we're below. Right? That's my zero potential. Above that is positive, below that is negative. Below that, H amount below zero potential. H is L cosine theta, and it's below, so it's negative. So this becomes minus MGL cosine theta. I'm going to give you a second to look at this. L was the length of the thread. It's swinging. Right? The mass is swinging. Now, what I'm looking for is H, not L, right? How far am I from zero potential line when I'm in position 1? All I care about is position 1 at this moment, writing this side of the equation. H, how can I find H from what I know, L and theta? So L is the length, theta is the angle that my pendulum creates with vertical line at this position, right? So creating that right triangle, looking at that triangle, knowing L and theta, H, I can find H. I can write H as a function of L and theta, which I know. Well, theta is something I'm trying to find. L is something that I'm given. Below zero potential line, so it's negative. If I was above, would have been positive. So that becomes potential energy at point 1. That's pretty much it. Let me put it this way. This is 1. Now at 2, let's see what happens. What's happening at 2? At 2, minimum angle theta necessary for the ball to swing to position 2. Now, the minimum is a key there, minimum angle theta. If it tells you find some angle theta, it could be anything. If you move it all the way up and let it go, obviously, not obviously, but most probably it reaches position 2 and it passes, right? It goes above this swinging M. Instead of stopping in this horizontal position, it might continue going up because there is still potential energy that needs to be kinetic energy that needs to be converted to potential energy. Now, minimum means how far I can move this pendulum mass M from vertical position. What's the minimum amount that I can move it away? How much is the minimum potential energy I can store into this pendulum by moving it away from vertical position? Right? Increasing its height, so I'm storing potential energy in it. How much is the minimum amount for which this mass reaches position 2? I don't want it to pass position 2. Right? I want it to reach position 2. Right? If I don't move this away from vertical position enough, if I don't store enough potential energy in it and let it go, this potential energy is not going to be enough when it is converted to kinetic energy to push this or take this mass all the way to this horizontal position. It might stop before that. The energy is not enough. So there is a minimum amount of energy needed to take this ball all the way to position 2. Right? That's the key. So that means that that my velocity at position 2 will be 0, right? For the minimum angle theta. Because if I move it further, I'm storing more potential energy. It's converted to kinetic energy and it's taking this ball all the way to position 2 and it's going to pass position 2. So it's going to have some velocity at position 2 because it's passing position 2. But I want the minimum. So this reaches position 2 and it stops there. I don't need more energy. That means that velocity at position 2 should be 0. T2 is 0. Minimum theta. Minimum theta. If it didn't say minimum angle, then this would have been a problem probably we couldn't solve, because any angle more than theta still does the job. More than minimum theta still does the job. Right. Now, V2, potential energy in point 2 at point 2. Well, that's pretty straightforward. The distance between the particle or the mass and 0 potential is L over 2, and is below 0 potential. So that would be minus mg L over 2. I can write it probably better. Minus mg L over 2. Now just put these two together. Right? T1 V1 plus T1 V1 is equal to T2 V2. So we will get minus mgl cosine theta is equal to minus mgl over 2. Get rid of m. We don't need g. Even l's are going to be canceled out. So all you get is cosine theta is equal to 1 over 2. And from there we can find theta. Right? Cosine inverse of 0.5 is 60 degrees, if I'm not wrong. Hopefully that's how I remember. Right. So this is the minimum angle. Now, if you take it 65 degrees and let it go, take it like all the way to 65 degrees theta, let it go, the mass reaches position 2 and it passes position 2 because you stored more potential energy in this mass by taking it farther. Right. All right, so that's part A. Pretty straightforward. If you want to do this with Newton's method, that would be a mess. And here, you only care about where you are position 1, where you are position 2. That's what you need to figure out. Geometry, logic here, minimum angle. Now let's connect this to some information we know from before. Right? Let's go look at the second part. Part B. Now, part B, we are told that if this ball is released at minimum angle theta, right? This minimum angle we determined here. Let's say the ball is released from that. Now we know theta is 60 degrees. That's a new piece of information we have. So if the ball is released at the minimum angle theta that we found from previous part, from part A, what is the tension in the string just before, and I can write it better, just before probably, just before and just after it hits the pin. So here is the situation right now. We have this pendulum. Let me quickly draw it here. It's somewhere here, M, right? Some angle theta. We found the minimum angle. And this is L. This is the pin. Once it gets to totally vertical position here, right, this is where it is. This is the pin. Now, immediately after and immediately before, we want to find out what is the force tension in the string. Same story. We just with the positions have changed. We talk about position 1 and position 2. Right? First part, well, first let's find the velocity. You know from example 1 that I'm going to need velocity. I won't do the way I did it for the first example. We did looking at free body diagrams and then figuring out I need velocity. We need the velocity in position 2, and you'll see why. So let's start with that. Right? T1 plus V1 is equal to T2 plus V2. Position 1, well, is a release from rest, same story as previous part A, so that there's nothing new there. V1 is, if I take this as, again, 0 potential, right? My datum for potential. This would be minus mgl cosine theta. Same story. Below, so it's negative. Position 2, let me just write it here. And position 2, T2, V2. Now, we have some velocity there. We don't know. Well, I'm going to put it as 1 over 2 m v2 squared. Probably I should do a better job naming this. So let's just use a different naming, so it's not confusing with the previous part. Let's say this is T3, V3. I'm looking position 1 and 3. Just change the naming. So 2 is what we studied before. This is 3. So that becomes T3, V3. Velocity at point 3, whatever it is. Potential at point 3 is minus mgl. Right? It's totally vertical. The distance the mass has from that 0 potential is the length of the string, which is L. Put this together, minus mgl cosine theta is equal to 1 over 2 m v3 squared minus mgl. You get rid of m. It's not what I want to do. You get rid of m. I cancel it from both sides. You can find the value. Let's move things around. You'll take GL to the other side, so you can write it as GL 1 minus cosine theta. I'm just moving things around. There is nothing really. 1 over 2 V3 squared. So from there, you can find your V3, velocity at point 3. That would be square root of 2G L 1 minus cosine theta. You know pretty much everything you need. G is G, L is 1, theta is 60 degrees, so you can find your V3. That would be 3.13 meter per second. So this is the velocity of this swinging mass when it gets to position 3. Now, let's see what is the story of just before and just after thing that we see there. Now, just before, remember, now we are looking for tension in the string. So we have to go back to free body diagram and the whole story about energy method. So just before, let's draw the free body diagram. This is this one. And then I'm going to put it on this side, kinetic diagram. So when I'm in position 3, what are the forces I have to put on my free body diagram? Isolate the mass and tell me what we have out of those 5 forces. We have tension, exactly. Thank you, Elizabeth. So we have tension upward. What would be T? What else? And we have weight. Exactly. Thank you. So we have weight. Oops. Downward. Just put this mg. Let's use, I guess the easiest way to do it is to use tangent normal. Right? Same situation we did with the first example. So let's take this as, I can erase that, as tangent direction. Take this as normal direction. If I do that, then you're gonna have 2 components on your kinetic diagram. This would be M AT, this would be M AN. Now, so writing, I'm just going to write the free body equation of motion in normal direction. There is really not that much going on in tangential direction. We didn't really take into account the air resistance or anything in that direction. It's an ideal case. So summation of forces in normal direction would be MAN. That would be T minus mg is equal to MAN. And well, we know AN, with AN being V squared over R. Now V squared is V3, velocity at this point. What is R at this moment? Remember, R is the distance between what we have and the center of rotation, whatever that object is rotating around. So what is R, value for R?
It would just be L, right?
Oh, it's just
R.
basically L, exactly. Thank you. So that's just basically L. Right? You have this circular motion, this pendulum swinging just before hitting the pin is basically swinging about this point. Oh, the distance is just L, the length of the string. So that you can just find what you want. T is equal to M G plus AN is equal to M G plus V3 squared over L. You know the values. V3, you find it from before, is 3.13. L is 1. M is given somewhere, if I'm not wrong. M is 2 kilograms, so it's 2. Just plug in the values. From there, you can find the tension in the string. Right? That will give you 39.2 newtons. All right. So what is the story of just after then? If this is just before, then what changes the moment this pendulum hits the pin? This is dynamics, right? That's the story in dynamics. At any given moment, things are changing. It's a dynamical system. So you have to take into account the state of the system at the moment you're studying the system.
The radius would be halved right after.
Exactly. Radius would be half. Thank you. So if I put just after, just after. Now, what happens in just after is that if I have my pendulum right there, I get at position 3, this is going to be position 3. When it hits this pin, the rotation is not, so remember before, the rotation was about 0.0. This was the rotation of the system. We took the radius is L, right? The distance between where we are and where the rotation is happening for that particle, about that. Once you hit the pin, now immediately after, this doesn't really, what happens is that this becomes your rotation. This is your rotation now. Right? The first part, the top part of the string stays vertical. The rest keeps moving. So this becomes L over 2. Now this is called O prime. This is your center of rotation. Right? This is where the rotation is happening about. So now you have a circular motion that is happening about point O prime, not O, after the string hits the pin. So everything is the same. Draw the free body diagram. Everything is the same. Free body diagram is the same. It's just after. So you're still in vertical position. A fraction of a second before and after. So the theta hasn't changed. You're still in vertical position. And that's the whole idea of saying just after. If you wait a little longer, it's going to go a little higher, and theta changes, and things are different. We're going to have a t that is in angle. But just after, the story is the same. Minus mg is equal to man. The only thing changes is with an would be v squared over r. In this case, would be v3 squared over L over 2. That will be your r. The radius of the distance you have from the point that you're having the rotation about. Now it changed. We just plug in the values. That'll be g plus 2 v3 squared over L. Then you'll get v3, L is 1, m is 2. I forgot what v3 was, 3.13. I can probably write it better. 3.13. That'll give you t as 58.9 newtons. Just after the pendulum hits the pin. This is the pin. So very straightforward approach. Very, very tricky things can be involved. Right? We're just playing around with words. Just before, just after. Things change. All right. Question on this one, guys. So we did start from typical kinetic energy, potential energy balance. This is a conservative system. There is no non-conservative force with the assumptions we have. Then we could calculate the velocity at point 3. Hopefully now you see why you calculate the velocity at point 3. You could start with free body diagram at in position 3, but then you would have realized that you need the velocity to be able to calculate the normal acceleration component. This could be very mind-boggling, playing around with very simple things that you already know, but paying attention to details. All right, let's see if I can fit in another example. I put the problem statement, see how it goes. If I don't get to solve it, I'll just post the notes with the solution for that problem. We have about 10 minutes. I just want to go over that example because that's the case with more than one mass. Things don't change. Story is the same. Everything is the same. You just have to take both or every mass you have in the system into account when you are looking into kinetic and potential energy for the system. So example, you have, draw it here. This one, let's make it as complicated as possible. Things are, and again, I know to you a lot of these systems look weird and you think, why do you even look at these systems? But in general, these are just simplified version of different mechanisms you'll see in a big machinery or different machineries that you design. So it's not that weird if you look at them within a machine, but it looks a little unusual when you just take out the system and just look at that part by itself. And that's just for us to make it easier to imagine what is going on and see what is going on in the system and be able to solve with what we've learned. So that one, it's attached to some, of course, there's a spring somewhere. There's a spring there attached to it. And then you have this one there. And there is a, probably I can do better. There is a thread here, a string there attached to this one, passing through this pulley. This is the support. Then you have mass. This will be mass A, and this will be mass B. Right, that's pretty much, I think, it. This distance is 0.3 meters, and this distance is 0.15 meters. A problem statement. Well, let's see what's going on first. So we have two masses, A and B. They are attached to each other using this string passing through the pulley, this pulley right here, and this pulley right there. B can go up and down while A is sliding on this bar. Right, and A is also attached to some support on the wall on the left with the spring. So when A moves to the left, the spring is stretched and B goes down. Right? When A moves to the left, spring is probably compressed if you go enough to the left, and B moves up. Right? The system of two masses. What we are told? We are told that the spring constant spring stiffness is K, 700 Newton per meter. The masses are MA is 14 kilograms, 14 kilograms, and MB is 18 kilograms. The bar is smooth, so no non-conservative force. There is no friction. The bar is smooth, and the general assumption is we always assume that we can ignore the friction in the pulley and rope system. It's a pretty big assumption because usually there is a good amount of friction between a pulley and a rope, but that makes solving it easier and let us focus on what we want to focus on instead of dealing with that friction there. So the bar is smooth, and generally there is no friction in the system anyway. At the instant
shown, again, dynamical system. It matters at which moment we're looking at it. The spring is unstretched, right? So when we are in this position, the spring is unstretched. The spring is unstretched. What else? And mass B is moving downward with so the velocity downward at 1 meter per second. That's the velocity of B at this specific position. Now the question is, how far is B moving, or how far is B moved, probably is a better way of saying it, when it oh yeah, my bad handwriting. Is how fast. That's why it didn't make sense. That's why it didn't make sense. How fast is B moving when it has moved 0.2 meters from its position. Right. So here is position 1 that we are in. This is position 1, like everything in this case. This is 1. This is 1. Now it moves, right? It goes here. We still have the same story right there. Then it moves down this much. This is A. This is position 2. So nothing changes. We'll have two masses, but we just have, it means that there are more things to take into account. But generally speaking, we have a system with no non-conservative force. Every force is conservative. We can write the conservation of energy principle. The only thing changes is that T1 and V1 should include both mass 1 and mass 2. Right? So when I write T1, let's start with V1, I guess. No, it doesn't matter. T1 and V1. Now V1, I have to look at both masses. All right? I have to consider VA1 plus this and VB1. Now, since we have two masses, what you can do to make your life easy, and that's the general approach you can follow, you can consider zero potential line for each mass separately. You don't have to have one zero potential line for the whole system. You can just say, this is the zero potential line for, let me find the color of it. So this is datum for mass A, and where we are, this is datum for mass B. We can just do it separately instead of having one and figuring out how things work. Just assume one datum for each mass. That makes your life much easier. So now, if that's the case, potential energy for both are zero. Right? At position 1, both of them are on their zero potential line. So that becomes basically 0. 0 plus 0. This is 0. Kinetic energy, well, the same story. TA1 plus TB1. Two masses are connected, so I can write it like this and then put it together. 1/2 MA VA1 squared plus 1 over 2 MB VB1 squared. They're connected, they move together, they have the same velocity. We only care about the magnitude of velocity, remember. So we can just put them together. This is for position 1. For position 2, I can write it here just to you have it. MA plus MB, because they have the same velocity. I'll just add 2 equations and then I say I'll call it V1 squared. Just put a note somewhere that we did this because they're connected, so they have the same velocity. Doesn't matter if the direction is different. This is energy method. We only care about the magnitude of velocity. 2, right? So V T2 V2. Right. T2 is well, let me start with T2 since it really TA2 plus TB2. Right, putting them together, you will get 1 over 2 MA VA2 squared plus 1 over 2 MB VB squared, VB2 squared. And they have the same velocity. We are in position 2, so I can just simplify it by writing MA plus MB V2 squared. The tricky part is the potential energy. Just give me a minute, then I'll post the rest of the solution when I post the notes for the lecture. But the thing that you have to pay attention here is, well, you have potential energy due to weight, potential energy due to spring. Weight, mass A is moving on its datum, so nothing from mass A. Mass B goes down, it's given, right? This height is given, it's 0.2 meters in the problem. So you know how much you go down. So that would be V, let me try to be more organized. V2, V, that did not, whatever. V2 is equal to, I will be able to figure this out. V2G is equal to V2 VA2G plus VB2G. A is 0, B is minus mg, let me write it this, minus mg 0.2. So the whole thing becomes minus 0.2 mg. V2 for the spring, right? Mass A has no spring, mass B has no spring attached to it. So we're just looking at mass A, right? That would be 1 over 2K S2 squared. Whatever is the spring is stretched. Now, how do I find that? That will be something that I'll add to notes and post it on Moodle. But the bottom line is, you have 0.15, 0.3, you can find the length of the spring in position 1, right? Just right triangle there. You notice both sides, so it's square root of 0.3 squared plus 0.15 squared. Length of the spring after the whole thing moved 0.2, so that 0.3 becomes 0.5, and then you have 0.15, you can find the length at position 2. You subtract those two, you get what is the length of this spring S2. Once you know S2, the rest is pretty straightforward. I'll finish this and post it on Moodle.